Okay, so today we're continuing section 11.3, and we're thinking about probability of multiple events. So we're going to use a Venn diagram to help us think about what we're working on today, the kind of probabilities that we're finding today. So a Venn diagram, you're going to have two circles and they intersect. So you'll have something over in this circle, something over in this circle, and this is the things that they have in common. So our problem says to create a Venn diagram where one circle represents numbers greater than 12 and the other circle represents prime numbers, and this is for whole numbers 1 through 20. So if we're thinking about numbers that are greater than 12, so numbers greater than 12 that are in 1 through 20, we're going to have 13, 14, 15, 16, 17, 18, 19, and 20. Those are all the numbers greater than 12 that are in 1 through 20. And then we need a circle that represents prime numbers that are 1 through 20. So if we're looking at the prime numbers, 1 through 20. Our prime numbers are numbers that have 1 and itself as their factors. So for our purposes, 1 is not a prime number. Most math books or math texts don't consider 1 a prime number. So we're going to skip 1. But other prime numbers that we have are 2, 3, 5, 7, 11, 13, 17, and 19. So those are our prime numbers. So now we can fill out our Venn diagram, because we're going to have one circle that are numbers greater than 12, and we're going to have one circle that are prime numbers. So the easiest way to fill this out, given our numbers that we have, is maybe to find what they have in common first. So our numbers greater than 12 and our prime numbers have in common, they both have a 13, they both have a 17, and they both have a 19. So in this middle section here, we're going to have 13, 17, and 19. And then now the rest of the numbers larger than 12 will go over here. So we're going to have 14, 15, 16, 18, and 20. And then the rest of our prime numbers are going to go over in this circle. So we've got our 2, our 3, our 5, our 7, and our 11. So that's how we would fill out the Venn diagram. So now there are a couple of questions down below. We want to find what the probability is that a randomly selected number from 1 through 20 will be one of the following things. So we want to know the probability that a number will be selected greater than 12. So we have to look at, this is our set. We're not looking at the entire set 1 through 20. We're looking at just our numbers that are greater than 12 and our prime numbers. So this is our set. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 numbers, right? So our whole set is 13. So we want to know the probability of getting a number greater than 12. So how many numbers greater than 12 did we have? We've got 1, 2, 3, 4, 5, 6, 7, 8. So for probability of greater than 12, we put our number of numbers that were greater than 12, which was 8, over our entire set, which was the 13. So you have a 12 out of 13. Or an 8 out of 13, sorry. Now we want to know the probability that you get a prime number. So probability of prime. Well, how many prime numbers did we have? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 prime numbers again. And that's still over our 13, which was our whole set. Now we want to know the probability that a number is greater than 12 and prime. So it's greater than 12 and it's a prime number. So those are our 3 middle numbers. Our 13, our 17, and our 19. They're greater than 12 and they're a prime number. So this gives us, we had 3 choices and that's still over our entire set, which was 13. So we have a 3 out of 13. Now we want to know a number that is greater than 12 or prime. So it's either going to be greater than 12 or it's going to be prime. It can't be both. So this is going to introduce our concept for today's sorting. So we're going to take our probability that it was greater than 12, which was the 8 over 13, and we're going to add the probability that it was prime, which is our 8 over 13 again. And then we're going to subtract when it was both greater than 12 and prime, which is our 3 out of 13. So when we simplify and combine our fractions, you're going to get 8 13ths plus 8 13ths, which is 16 13ths, minus the 3 will give you 13 over 13, and that just equals 1. So this kind of helps us think about what we're going to be talking about today. So we're going to be talking about mutually exclusive events and inclusive events. So a mutually exclusive event is when 2 or more events cannot happen at the same time. So there's no way for the 2 things that you're talking about to happen at the same time. An inclusive event, however, is when 2 or more events can happen at the same time. So looking at our Venn diagram problem, we had that we were looking for numbers greater than 12 and then prime numbers through 1 through 20. So we had numbers that could be both. So our Venn diagram example is an inclusive problem, because we had numbers that were both greater than 12 and prime numbers. And notice today that in our probability, we have an or. When we're talking about mutually exclusive or inclusive events, we're going to have an or. Where yesterday we had ands. When we were talking about independent and dependent probabilities, we had ands. So today we're going to have ors. So down below kind of helps us think about whether events are mutually exclusive or whether they're inclusive. So the first one says, having black hair and wearing glasses. Would those be mutually exclusive events or inclusive events?
Inclusive?
Those are inclusive because those 2 events can occur at the same time. You can have black hair and wear glasses. So those are inclusive events. Now the second one, having blue eyes and having brown eyes. Are those mutually exclusive or are those inclusive?
Mutually exclusive.
Those would be mutually exclusive. Now some could make the argument that it's inclusive because you could have an eye of each color. However, normally you only have one color eye. So it's a mutually exclusive event. Those are mutually exclusive events. The third one, having a number greater than 12 and being a prime number.
Inclusive?
So that's inclusive because that was our Venn diagram problem. We had 13, 17, and 19 that were both greater than 12 and prime numbers. And then our last one is being a multiple of 4 and being an odd number. Are those mutually exclusive events or inclusive events? They're what?
Mutually exclusive.
They're mutually exclusive because if it's a multiple of 4, we know that 4 is an even number. So if it's a multiple of 4, those are all even numbers. And an even number can't be an odd number too. So those are mutually exclusive events. So at the top of the page, it gives, if we're thinking about the Venn diagrams again, it gives an image of what we can think of mutually exclusive and inclusive events looking like. So if our events are mutually exclusive, our two bubbles are never going to touch. There's no overlap. They're completely separate events. For inclusive, however, we can think of our traditional Venn diagram, where we have the two circles and we have that section of overlap. That section where they can be both things. And we also have our equations for finding these probabilities. So if our event is mutually exclusive, we're going to take the probability of our first event and add it to the probability of our second event. If it's inclusive, we're going to take the probability of our first event, add the probability of our second event, and then subtract the probability of when the events coincide, or when our number or whatever we're happen to be talking about can occur in both events. So again, notice that today we're using ORs. So ORs will tell you that you need to think about a mutually exclusive or an inclusive probability. And also notice that today, when we use OR, we're adding and we're subtracting. Where yesterday when we were talking about ands, we were multiplying probabilities. So you need to make sure you know what sign goes with what probability. So example 1 is going to give us some examples of mutually exclusive and inclusive. So example 1 says we roll one die. We need to find the probability of each event and identify it as inclusive or mutually exclusive. So part A is asking for the probability that we roll a 1 or we roll a 6. So I like to put what my set is right away. So we're rolling one die. So I know that I can get a 1, I can get a 2, I can get a 3, a 4, a 5, or a 6 on a single roll when I roll a die. Those are my options. So thinking about problem A, it wants to know the probability of rolling a 1 or rolling a 6. So are these events mutually exclusive or are they inclusive?
Inclusive? Inclusive?
Why would it be inclusive? Can you roll a 1 and a 6 at the same time?
No.
Because we're only rolling one die. So you can't roll a 1 and a 6 at the same time. Only one number is going to come up on the die, right? So that's going to be a mutually exclusive problem. Because those two events aren't going to occur at the same time. So to find this probability, we need to find the probability of rolling a 1. So the probability of getting a 1, how many times can you get a 1?
6. 1 out of 6.
Yeah, so you can only get a 1 once, and that's out of your 6 different options. So your probability is 1 out of 6. And then we also need the probability of rolling a 6. So what's our probability for rolling a 6?
1 to 6.
1 out of 6 again, because there's only 1 6 on a die. So now, using our equation that we were given for mutually exclusive events, we're going to take the probability of finding the 1, or of rolling a 1, and we're going to add it to the probability of getting a 6. So we're going to get 1/6 plus 1/6. So that's going to equal 2/6. And we need to reduce this fraction,
1/3.
so we're going to get 1/3. So you have a 1/3 chance of rolling a 1 or rolling a 6. Part B wants the probability of rolling an even number or rolling a prime number. So are these events mutually exclusive or inclusive?
Exclusive, because you can roll a even and
So they're inclusive because you can roll an even number and a prime. And that number is 2. 2 is prime and it's an even number. So these are inclusive events. So we need to find the probability of rolling an even number. So how many even numbers do we have? 3. We've got 2, 4, and 6. And that's still out of our 6 options. And then we need to find the probability of rolling a prime number. And again, prime numbers are numbers that are just have only factors of 1 and itself. And again, we're not classifying 1 as a prime number, so we just leave 1 out. So other prime numbers, we've got 2, 3, and 5 are other prime numbers. So again, we have a 3 out of 6 chance. Now, because we said this was an inclusive event, we also need to find the probability of when it's even and prime. And we said that 2 was our only choice for an even and a prime number. So we have a 1 out of 6 chance of finding that even and prime number. So now to find the probability of even or prime, we're going to take the probability of even plus the probability of prime, and then we're going to subtract the probability of even and prime. So that equals our 3 over 6 plus our 3 over 6. And then we have to subtract the 1 over 6. So 3 over 6 plus 3 over 6 is 6 over 6. And then minus 1 over 6. So we get 5 over 6. So you have a 5 out of 6 chance of rolling an even number or rolling a prime number. Part C. We want to find the probability of a multiple of 2 or a multiple of 3. So are these events mutually exclusive or are they inclusive? Rolling a multiple of 2 and rolling a multiple of 3. Or rolling a multiple of 3. These would be inclusive events because 6 is a multiple of 2 and it's a multiple of 3. So we have an event that could occur in both situations. So that's what makes it inclusive. So we're going to take the probability of it being a multiple of 2. So our multiples of 2 are 2, 4, and 6. So we have a 3 out of 6 chance of rolling a multiple of 2. Then the probability of getting a multiple of 3, our multiples of 3 are only 3 and 6. So we have a 2 out of 6 chance of getting a multiple of 3. And then again, because we said that it was inclusive, we have to find the probability of getting a multiple of 2 and a multiple of 3. And like I said, 6 is a multiple of 2 and a multiple of 3. So you have a 1 in 6 chance of getting a multiple of both. So setting up our probability again, our probability of getting a multiple of 2 or a multiple of 3 is the probability of getting a multiple of 2, which is 3 over 6, adding the probability of getting a multiple of 3, which is 2 over 6, and subtracting the probability of getting both, or of both events occurring at the same time, which was our 1 out of 6. So we get 5 out of 6 minus the 1 out of 6, which gives us 4 out of 6. And again, we need to reduce this fraction. So you get 2/3. So the probability of getting a multiple of 2 or getting a multiple of 3 is 2/3. Example 2. Example 2 gets into playing cards. So this one's going to be a little bit confusing just because we have to think about what cards we have. So a card is drawn from a standard deck of playing cards. We need to find the probability of each event and identify an inclusive or mutually exclusive. So we know that a standard playing deck has 52 cards, right? So there are 52 cards. So 52 is our whole set. So part A asks us to find the probability that we get a heart or an ace. So are these events mutually exclusive or inclusive? Can you draw a heart and an ace at the same time? Yeah, because there's an ace of hearts. So these will be inclusive events. So we need to find the probability of getting a heart. So we have to figure out how many hearts are in the deck. Well, we have ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, and 2. So we have 13 different hearts. And that's out of our 52 total cards. Then we also need to find the probability of getting an ace. How many aces are in a deck of cards? 4. There's one for each suit. So that's a 4 out of 52. And then because we said it was inclusive, we have to find the probability when it's a heart and an ace. Which, like I said, there's one ace of hearts out of your 52 cards. So to find the probability of a heart or an ace, we have to take our probability of a heart, which was the 13 over 52, add the probability of an ace, which was 4 over 52, and subtract the probability of when they occur together, which was the 1 out of 52. So when we add these, we get 17 over 52 minus 1 over 52. So you get 16 over 52. We can reduce this fraction, and it becomes 4 over 13. So you have a 4 out of 13 chance of drawing a heart or drawing an ace. Part B wants us to find the probability of drawing a face card or drawing a number card. Are those two events mutually exclusive or inclusive? Can you draw a face card and a number card at the same time? No. So these are going to be mutually exclusive events. So for mutually exclusive events, we need to find the probability of a face card. So face cards are King, Queen, Jack. So you have 3 different face cards for each suit. There are 4 different suits in cards. So 4 times 3 is 12. So we have 12 different face cards. So you have a 12 out of 52 chance of getting a face card. And then we need to find the probability of getting a number. So number cards, again, there are 13 numbers. No, there are 9 numbers. Because you have 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 9 number cards for each suit. So you have 9 times 4 gives you 36 number cards total. So probability of drawing a number is 36 out of 52. And because these two events are mutually exclusive, those are the only 2 probabilities that we need. So probability of a face card or a number equals the probability of getting a face card plus the probability of getting a number. So we have 12 out of 52. We're adding the 36 out of 52. So we get 48 out of 52. And again, we can reduce this fraction, and you'll get 12 out of 13. So you have a 12 out of 13 chance of drawing either a face card or drawing a number card. And then part C. Find the probability of drawing an odd number card or drawing a red card. So are these two events mutually exclusive or are they inclusive? They're inclusive because there are odd numbered cards that are also red. For example, you have the 3 of hearts, which is red. You have the 3 of diamonds, which is red. So there are cards that could be in both events. So this is an inclusive event. So we need to find the probability of getting an odd card. So our odd numbers are 3, 5, 7, and 9. So we have 4 odd number cards for each suit, which again there are 4 suits. So 4 times the 4 gives you the 16. So there are 16 out of 52 cards that are odd. Now we also need to find the probability of getting a red card. There are 13 different choices for cards in each suit. So if we know our red cards are our hearts and our diamonds, and we know that we have 13 of each, we have 13 times 2, gives us 26 out of 52 cards that could be red. Now, we also said that this was inclusive, so we have to find the probability of when it's odd and red. So again, we said our odd cards were 3, 5, 7, and 9. So we had 4 odd cards for each suit. We have 2 red suits. So we have 4 times 2 gives us 8. So there are 8 out of 52 cards that are odd and red. So now to find our probability of odd or red, we take the probability that it was odd, which was our 16 out of 52, add the probability that it was red, which was 26 out of 52, and subtract the probability that it was both, which is our 8 out of 52. And you should get 34 out of 52. And then this fraction reduces to 17 out of 26. So there's a 17 out of 26 chance of drawing either either an odd number or a red card. The last page, the front and back, is your homework. I hope to have it on YouTube soon.